Okay, maybe we can start. So, hello everyone. So, good afternoon. So it's my pleasure to introduce the speaker today, Professor Erdös from ISTA Australia. So Professor Erdös got his PhD in Princeton in 1994, and after that he worked in Zurich in Courant Institute in Georgia Tech before he became the chair of applied mathematics in the University of Munich, and now he is a professor in IST Austria. And so he's well known for his work on random matrix theory, on quantum many-body system, and random operators, and many other things. And in particular for the topics today, I would like to say that he has made a fundamental contribution in understanding the universality of eigenvalue statistics for large random matrix. And for which he was awarded the Leonard Eisenberg Prize in 2017 by American Mathematics Society. So I hope everyone can enjoy talk. Please.
Thanks very much. Thanks for the nice introduction. Thanks for the invitation, especially to Serena, who worked hard to invite me here. It's a beautiful place. Actually, I've never been here. Very fair practice. There are so many mountains around. I'm coming from Austria, but in Vienna, I will show a picture of the size of the Austria. But our mountains are not as high as the mountains here, at least the ones which I see from my own building. Okay, so let me just introduce. I will give an overview talk because I understand that the audience is quite neat. So we talk about several results on a high level, superficial level. So there are several papers whose results we will mention, and these are my collaborators in various orders. We have current or former postdocs and students. So one of them especially is important. This is Giorgio here. I'll show him. He's sitting there, although the picture is something like 8 years old. It's a little bit, it's changed a little bit, but so he's one of the main collaborators. Okay. This is ISTA Austria, so this is a research institute which is actually quite similar structure. It's to the GSSI. In a sense that this is a graduate institute. We don't have undergraduate students focusing on natural sciences. We also do have the biology, but of course what is important for me is the mathematics and physics part, which we also have quite a strong group. And as you see, I mean, we are also among the mountains, but not so much mountains. It's the Vienna woods, it's other of Vienna. Okay, so let me come to the topic. So I usually like to introduce the topics of random matrices with this kind of provocative title. That is a question of what mathematicians fail to ask, and we have to wait until a physicist named Eugene Wigner came up with the natural question. And the question is this one, that what can be said about the statistical properties of the eigenvalues of a large random matrix. So these are some universality emerging there. So the idea that the picture, the basic setup is this one, that you have an n by n matrix, where we talk about square matrices, n will go to infinity. We talk about large matrices, and we compute the eigenvalues, and there are n eigenvalues altogether. And imagine is that the matrix will be random. Basic invention of Eugene Wigner. Make it random. There are various ways to make it random, but the easiest way to make it random, and that's sort of what today's talk, is that you choose the matrix element to the IID random variable. So IID stands for independent, identically distributed, except that because it came from Eugene Wigner, who was interested in quantum mechanics, and he was thinking about the random matrix as a Hamilton operator of some quantum system. So there's only one constraint, is that the H has to be symmetrical to the Hermitian. So depending on whether we talk about real matrices or complex matrices, either symmetric or Hermitian conjugate matrix. So and then the Wigner has this vision, that's the question of people, other people have to ask. He had the vision that you have this random matrix, and this random matrix, although nobody has seen that in reality, in real life, such a matrix that still can be useful to understand certain certain properties of the eigenvalues. And the basic reason why it's true is that there's an universality phenomenon. So the universality phenomenon tells you, and we will see that if you ask a certain type of question, if you ask a specific question about the eigenvalues, then the answer to this question will be essentially independent what kind of matrix you put in, about the original matrix, in the sense that it's basically independent of the distribution of the matrix element. So, independent identical distributed random variables, they have to choose a distribution, for example, Bernoulli or Gaussian and whatever your favorite distribution. And according to the distribution, according to this thing, you fill in the matrix. And then you ask a question about its eigenvalues, which the answer to this question will be independent whether you use a coin tossing, whether you use a dice, or whether you use Gaussian, and so on. And of course, I mean that there's a big vision that there is such a meaningful question about the eigenvalues. But even more importantly, is that Wigner conjectured and visioned this, that the question, that the type of question that comes out of universal is an important question in physics. So the question what came out is that the eigenvalues, of course, primarily, but even more importantly, the eigenvalue differences. So we will see that it's not really the lambda 1, lambda 2, lambda 3, and so on themselves, which are so specific or so special, but rather the differences is lambda 1 minus lambda 2, lambda 2 minus lambda 3, there are so-called gaps that the work that comes in physics. And if you know physics, then you have eigenvalues correspond to energy levels of the quantum system, and the energy differences are the really important, and those are the possible quantum mechanical reaction incoming photon and increase on a photon and so on, and the frequency energy of the photon is determined by the energy difference, not by the channel. So this is the model, and then of course the question, the basic vision behind that, and that's what mathematicians fail to ask the question that everything that I told you so far, we talk about matrix, eigenvalues, randomness, and so on. This had been known well before the 50s, so this was done in the 54. But all the ingredients were known 50 years before that. We have probability theory like Kolmogorov was completely experimentalized in the 30s. So mathematicians could have asked this question, but they didn't ask it. And that's because probably at that time, probability theory was looked down. It was not considered part of mathematics, but not of serious mathematics. Of course, nowadays the art has changed, and nowadays, basically, whatever object is studied in mathematics, there's a randomized version of that. We talk about random functions, random groups, random graphs, random topology, and everything can be random, and you can reach on that thing. As new types of thoughts and new phenomena occur, but somebody had to start with this argument. I think we should give a credit to using Wigner to randomize mathematics. Okay, so now this is the very basic setup. Let me mention the basic questions that we look at. But let me go back to the basic probability lecture. There is no matrix on this slide. I want to indicate to you what the type of questions you can usually ask in probability theory, and we'll ask similar questions in random matrix setup. So for simplicity, let's just look at this simple case that it has an independent identical distributed random variables x1 to xn, just normalize them to the expectation 0 when it's long. And then the first question, the first non-trivial theorem, first serial theorem of the learning probability theory is a law of large numbers, which tells you that if you have these independent random variables, you add them up, and you get a quantity of order n, so you divide by n, and then this quantity as n goes to infinity converges to the deterministic number, which in that way is the expectation. These are very, very general phenomena, it's also called self-leveraging in physics. So the important thing is that we start something with something which is random, but then as n goes to infinity, becomes more and more deterministic. Now the next level is the central limit theorem, which talks about the fluctuations about the law of large numbers. So here you take the sum, but you normalize it differently. If you normalize it by n, then the whole thing converges to 0. But if you normalize it by something else, and it happens to be a square root of n is the right normalization, and this quantity becomes again non-trivial, But the limit is not a deterministic object anymore, it's not a number, it's actually a distribution, we can take a standard Gaussian distribution. And here you already see this phenomenon what we call the universality earlier, that no matter what the initial distribution of the axes were, under some very weak conditions, nevertheless, no matter what the initial things were, the outcome would be always the normal distribution. The normal distribution is universal. If you ask the right question, sum up and divide by the square root of n, but you ever get a standard variation. Now, so these two things are basic material and probability theory. Here's one more, which maybe you don't know so, but maybe it's a little bit higher level in probability theory when they teach it to you. So here it's yet another refinement of the previous story. So you take the sum again, and if you divide it by square root of n, then the whole thing would be a fluctuating object with a normal distribution. But now you change n, so n is increasing, and you ask yourself how big this sum could be, how big this normal sum could be, and the normal distribution is a tail, so in principle this sum could be much bigger than all the one with very small probability. So now the law of iterative logarithm catches this extreme fluctuation, and it says very precisely, it says that if additionally to a square root of n scaling, you divide it further by a quantity which goes to infinity very slowly, the double logarithm, log n. If you do that, then the meaning for that, the extreme situation, will converge to a non-trivial number in this one, because it's not great. But on the other hand, the ring soup goes to plus 1. So this case, so the extreme fluctuation happens on the scale of this additional square root of log n. Okay, that's the law of iterative logarithm. This is called the external fluctuations. And there's one more typical theorem which you can learn in probability theory. This is called the external statistics. This asks, again, you have independent random variables. Instead of the sum, it asks for the maximum of the individual random variables. Now, depending on the tail of the distribution, sometimes the maximum can be much bigger than the typical value. It can happen, and this question asks you how much the maximum, how big the maximum can be as n goes to infinity. So now, of course, I mean, you have something which is, so this can typically goes to infinity. So you do the usual type of rescaling, because we are looking for universality, looking for the typical fluctuation of this maximum, but for that we have to vary. So first we have to subtract some constant, which is supposed to be exactly the expected value of this maximum. Similarly, as well, you have to subtract the expectation of x. Then you may have to normalize by a normalizing factor, a prefactor of dn. an and dn may depend on the distribution. But if you choose them properly, then as n goes to infinity, this shifted and rescared random variable will converge to a non-trivial distribution. Non-trivial is neither 0 nor infinity, but something a non-trivial distribution like the central limit theorem is. And this non-trivial distribution happens to be again a universal distribution. It's called a Wigner random variable, which is a double exponential distribution function. So that's and here again you have this universality that again essentially not completely, but essentially this statement is independent of the distribution of the axis. an and dn depends on the distribution, but after you do the rescaling, the limit below does not. Okay, and just a feeling how it looks like. So if the axis happens to be the normal random variable itself, then these are the two formulas for the an and the dn. An ugly thing, but it has a structure, especially an has a three-term structure. So this actually the expectation, the maximum of the Gaussian random variable, because that the square root of log the leading formula, the log value, square root of the constant divided by the square root of log. So this is a very precise thing, and these numbers here, these formulas depend on the fact that it's going to be a normal distribution, but the fact that after this scaling I get the dumbbell, it's universal. This is sort of a very basic questions and answers in probability theory. Now we look for similar questions and answers in the context of randomness. And we will do mostly having randomness to very few pictures about randomness. So let me start with a few of the two classical results about Hermitian random matrices. So the most important object is what we call the Wigner matrix. It's basically, I told you what it is, but here's the proper definition. It's a Hermitian random matrix whose entries are independent, identically distributed up to the Hermitian symmetry. And then we have a certain normalization, expectation 0, and the variance is chosen to be 1 over n. This is a convenience, but under this scaling, it turns out that the spectrum of the matrix remains orderable. So it either shrinks or goes up to infinity, as I just told the figure. And the first non-trivial theorem in this business is the Wigner semicircle law, which says the following: that look at the empirical density of the eigenvalues, which are we call the density of states. This converges to something deterministic and like a universal deterministic function, which is the semicircle function. So the picture shows with the explicit formula for that. So what it says is that you have the bars, this origin bars, these are the eigenvalues, which are of course random, depending on the realization of different points of this here, the eigenvalue. But if you draw the histogram, you do the statistics of the eigenvalue, the density of them, then the histogram of this random sample will converge to this very universal semicircle. Okay, so that's the first case. It's about the density of states, how very crudely how the eigenvalues macroscopic scale, large scale, how the eigenvalues different. Of course, I mean the statement of information is a mathematical theorem, don't have the convergence, but this convergence here is converges to this weak convergence. So weak convergence meant that we test it against sufficiently now smooth quantity. Okay, and if you wish, then this is a type of law of large number result in the previous sense, because what you start with is random. You have a bunch of a random density of it. So random eigenvalues, the random eigenvalues determine a density of eigenvalues, density of states measure, which is a random measure, and this random measure converges to a deterministic measure. Okay, so this is the first level. Now the law of large number. Now more it was also a very nice theorem, but more importantly, Wigner had a revolutionary observation, so mentioned in words, is that if you ask a different question, which is about the gaps, so not the eigenvalues themselves, but the difference between neighboring eigenvalues, it's a much better, even better object, better meaning to be more universally. It's very robust, and the distribution of the gap statistics really independent of everything. It depends only on the independent of the distribution matrix, and so it only depends on one thing, whether the initial matrix was real symmetric or complex Hermitian. So in order to formulate it a bit more precisely, you have to scale the things properly. So you talk about two eigenvalues, there are two neighboring bars in this picture. The typical distance between two neighboring eigenvalues is 1 over n. In order to get something meaningful, you have to take the difference on times n. You also multiply by the density to account for the inhomogeneity space in the spectrum. If we scale it properly, then this quantity is a random variable. This will converge as a random limiting distribution. So what you see here is the origin, some histogram of sampling the gaps in the actual measure, in the actual numerical experiment. And then the green curve is the limiting distribution of that intensity of this scale gap distribution angles. And here there's a formula. This formula is a bit cheating. The explicit formula here is a formula what Wigner computed for this gap distribution. This is a completely universal function. It's a little bit cheating that it's not completely correct, because what Wigner did is exactly what a physical physicist would do. What Wigner did is that, I mean, he was interested in n by n, and he wanted to know n goes to infinity, but that was too hard. And Wigner could do the semicircle law, which is a much easier question, but he could not do this picture. So because he didn't compute it for large n. And then he said that if you're a physicist, then he said, okay, n equal 1 is too small. And you don't see much, but if n equal 2, then maybe n equal to almost like n infinity. So he did that. He computed 2 by 2 matrix. 2 by 2 matrix was only 2 eigenvalues. computing that, like that, and now you can picture the distribution. This is this curve. So you want to do a nice number to your students, and one maybe a student said that anyway. Then you can compute that the two-by-two matrix is Gaussian, and this is the distribution of the difference of your. But then it turns out so that the true curve is not there. The true curve is an ideal explicit formula, which is much more complicated, and we can get out it here. But actually, this function, this explicit function of 10 per m equal to, is very precise. It's almost a 3% close to the true curve. Okay. So now, this was done actually later. So the true curve was computed by Wigner-Dyson and Meta in the 60s, and 10 years after Wigner, they computed the two angles to infinity. But then all these things were done only for one single distribution, when you call a Gaussian matrix element. It just happens to be in the general phenomenon of mathematics and physics, is a Gaussian, but one of the best distributions for physical calculation. So of course here you could take a random matrix, Wigner matrix, and the matrix element would choose them to be Gaussian. This is another special for the Gaussian military from the GUV in short. And for that matrix, for various algebraic reasons, you can do explicit calculations, but only not trivial. This is what Wigner-Dyson did and compare. But then the conjecture, going back to Wigner's vision, was that this gap distribution is independent of that distribution of the matrix elements, and that was an open question for almost 50 years, and eventually managed to prove it. So what we proved is that the same curve, the same green curve, which was computed from Gaussian matrices, holds also for basically for any matrix which has independent identifier distributed. Okay. Now, here I was talking about the bulk. Bulk here means that you take eigenvalues away from the -3. You can feel that around the edge, near the spectra or something else happens, just by the fact that as you approach to the spectra, the gap, the distance between order and eigenvalue is changing. It's not 1/n anymore. It's 1/n to the 2/3. So it's a different gap distribution. You have a different prefactor. And also the universality behaves differently. But still there's a universality, so there is something that's called the edge universality, which refers to the local statistics around that point. And this is known, this has been invented and found much later in the 90s by Tracy and Widom. So it's a different type of universality. Same matrix, but a different regime, branch regime. And interestingly, the Wigner-Dyson meta conjecture that was set up in the 60s at that time, it had infinite around the edge, and then when it was much harder to prove. By the edge universality, the edge phenomena was found in 1993, I think, by Tracy-Widom, and a few years later, Washington managed to prove it. This was actually 3 years decreases. So both of them also say that both of the distribution, this here, this picture, and the analogous curve for the edge of Tracy-Widom distribution, these are both of them are a completely new distribution. Nobody has seen that before. It's not like that. It's on the normal, it's on the Wigner, it's on the diagonal, it's nothing which probably to theory before. It's something new, and it's never that's universal. Basically, about our real world. And in particular, this reflects one key property of the eigenvalue, which is a strong correlation. So, and the eigenvalues you can think of as a point process as well. But these points here, they feel each other. There is a phenomenon which is called eigenvalue repulsion, which tells you that neighboring eigenvalue, okay, there is 1/n distance between them, but the probability that two eigenvalues get much closer than 1/n is suppressed. This you can see from this part of this curve. This is the density of the gap. And the fact that the density goes down to 0 here is equivalent to saying, this is equivalent to saying that, let's try to close it, and just kill it. So this is the fact that this density goes down to 0, this is equivalent to what I said, the level of function, where the probability that the gap is very small is suppressed. This is a phenomenon which indicates that the eigenvalues knew each other. The spectrum of the matrix eigenvalues, the principle that eigenvalues are random, they are random, but then they are strongly correlated close to each other. Okay, so that's something which is an important feature of this model, especially if you compare it with other point processes. So I mean, what you see here is a bunch of points, a bunch of random points. So your first natural instinct would be to function probability field, but maybe they're completely random, like a Poisson process. Poisson processes are analog or point processes are analog to fully independent objects. The Poisson point process is completely independent. You put down points on a lot. And this one is not like that. This is here the points feel each other very strongly. So that's why it's a very hard problem. You know, more independence is probably the problem is easier. But here the object that you look at, or the level of the eigenvalues, it's very, very strong. Okay, so here's another picture, roughly speaking, how it looks like. So on the top you see again the semicircle law. And in order to see these local statistics, the gaps, for example, you have to do this zooming. So you fix some energy here in the middle of the spectrum, you zoom it out, you have to increase it by a factor of 1/n, and then you see a point process. Now the point process is scaled after this scaling such that the typical distance is order 1. You can hope that this bunch of point processes, the sequence of point processes, also has a limit. So far I was talking about the gap, the distance, the difference between two eigenvalues, but you can elevate it a little bit higher level. You can talk about convergence of point processes like that. And after this local scaling, it also holds that the distribution of these points here, the point process converges to something like that. And the same happens in the edge with a different scaling, and the limit flow is different as for the Tracy-Widom distribution. But philosophically, morally, the same thing happens with the universal picture emerging independent of the original distribution. And actually, there is a third statistics, and where the Wigner-Dyson and Tracy-Widom have been known for many years. There's a third universal statistics, which was not very well known. This is called the Pearson statistics, which comes at the cubic class of singularity. Maybe I will have a picture later on. The semicircle does not have this type of single. The semicircle is basically everywhere it's positive, except at the edge, when it goes down to 0, and then of course goes down to the square root singularity. And this singularity type determines the Tracy-Widom distribution. So if the density happens to vanish at another power, then we expect something new. And indeed, there are situations when the density inside the semicircle behaves like a cubic class, and then around that point, the local eigenvalue distribution will yet another universal Pearson distribution. I think that is that. So now, so far I was talking about Wigner matrices, but then in the last decade, all this theory has been extended for much more general ensemble, because remember the original vision of Wigner was that the matrix is just a whole model. The idea is that eventually we wanted to model quantum mechanics, and basically any quantum problem with this idea. But the basic picture behind it is there are sufficient to be large matrices which have sufficient amount of random, not sufficient amount of randomness. If there are sufficient to be matrix with sufficient randomness, then the eigenvalues will behave in this universal. Now, in order to get closer to this very vaguely formulated conjecture, we started working on extending the original model generally in various directions. And remember that the Wigner matrix was defined by three adjectives: independent, identically distributed, and also zero expectation. Now you can start removing these restrictions one by one. So, for example, if you remove the zero expectation from that, that's equivalent saying that you take a Wigner matrix of an active at a deterministic matrix. The expectation, the matrix of expectation. So this already takes something out of your comfort zone, where the non-trivial expectation changes by time on the semicircle. It's not a semicircle anymore, then the density will depend on it. Then you can start playing with the identical distribution. So the variance doesn't have to be 1/n. do some modulations on the density. And also you can remove the independence. You can pass on the correlations and matrices which have specific correlations. So all these things one can do. Then in another direction, one can talk about sparse matrices. Sparse matrices in the Tudor distribution, which is a very high probability of 0, with some small probability of such a very big number, like usually we get a matrix with lots of 0 and a few non-zero numbers. For example, this is the adjacency matrix of a random graph, a sparse random graph, with lots of connections to combinatorics. Then you can start putting in some clever spatial structure. The Wigner matrix, with the fact that the matrix elements are I and B, is a mean-field model in physics. So mean-field means that you don't really see the difference between the I, J, and K and matrix element. It doesn't really matter whether you go from I to J, in the transition sense of the matrix, or you go from K to L. The transition rate, quantum transition probability is exactly the same for the same distribution. Now, this is not very linear, because I need to know the two-type model. So if you try to depart from the model, then you start creating matrices which are huge property to 0, and you can structure. For example, band matrix and matrix, which is essentially 0, and a certain bit around the diagonal are non-zero. Like in X-ring case structure, diagonal matrix, so you can go into that direction, and this way you put in more space structure. You can also talk about heavy matrices and many other listed all these things. But then there's a very general philosophy behind this picture, is that there is this universality of the local eigenvalue statistic. Local eigenvalue statistics in this point process appropriate to this scale. And this holds, this is universal, if you have for any sufficient random matrix or even operator, as long as you have the so-called delocalization. Now, the concept of delocalization goes back to Anderson, goes back to random Schrödinger, to introduce random Schrödinger here. But this another very strong, physically very strong motivated research direction in mathematical physics. So if you take a random Schrödinger operator or Gaussian plus a random potential, then there are two versions. One of them is the famous Anderson localized version, meaning that the eigenfunction is spatially localized, or contrary to the localized version. Whether you are in one regime or the other regime, that depends on the size of the parameters and the phase transition between them. But the point here is that if you are in the delocalized regime, so localized versus delocalized can be defined for basically any random operator, which are underlying space structures. So as long as you are in the delocalized regime, you are supposed to be in the regime that also this Wigner-Dyson and before. If you have a random operator, somewhat reasonable random operator whose eigenvectors are delocalized, then you could expect reasonably expect that the eigenvalues with this appropriate scale for the web distribution. Okay. So now let me just show how it looks like a little bit more precisely. So I'm looking at the situation when the expectation is non-trivial. So this is the expectation matrix, and even the variance is non, and even I have some correlation. So this S here is the so-called covariance matrix or covariance tensor, which just tells you that it encodes all the information about the covariances of anything matrix elements. It's formatted in such a way that an operator, which is defined in the space of matrices according to this formula. So there's the expectation of H and H, expectation remove the H's, and then you have something which is a linear operator, linear mathematical that of the space of matrices. And variance matrix, and then you want to figure out what is the density, how the sum takes something else. And here's the procedure to get the density, kind of a one-step procedure. First, you have to solve the so-called matrix Dyson equation. This is an equation which looks like that. An equation whose first of all, it is a parameter z, this is a spectral parameter, which is always in that frame. And this equation is an equation for an unknown matrix M of z, matrix value function M of z, and it satisfies this equation 1 over n or minus 1 over n for z minus a plus the s acting on this covariance operator acting on any side. Beautiful application. It's a highly non-trivial application. It looks very compact, but remember, M is a matrix, so it's like it looks like a qualitative equation. It's a qualitative equation. Matrix is 1 over the unknown equal to a linear function of the unknown. But M is a matrix, so this equation has many solutions, lots of solutions. But then M will be actually a relevant of somebody, approximately. So we put the side condition that the imaginary part of M as a matrix has to be non-negative. And under this condition, it turns out that this equation is one unique solution, not the solution that we are looking for. So you pick this solution M, and then you go back to this line. So now take this M, you take its imaginary part, you take the trace of that normalized space, this bracket is the normalized space, and then you take the boundary values. This is the function of the upper half plane, x plus r eta, and then let eta go to 0 for the boundary value of an analytic function depending on that. The boundary value of that is a real value function, rho of x, and that's the density. That's the density of space. That's what we value of that of the eigenvalues and distributed. There's a nice picture. So what you see then show the picture down. The picture down show a situation where you are all density, there are all various versions of rows. And then I change one parameter, I'm putting some parameter in the data. I played a little bit with the parameters in such a way that I go from a situation when I have three disjoint and this three disjoint support the three disjoint intervals, and I move the parameter in such a way that the intervals close, so the three separate bonds eventually close, and then I continue moving the parameter and then you do something like that. And then the moment when the two bonds meet, then you have this cusp singularity. So at that point, it turns out it doesn't look like not easy to see, but at that point, you have a cubic behavior that's and we have a theorem years ago, we proved a theorem which says that these are the only possibilities. So if you solve the equation, you do this procedure, solve this complicated equation, choose the unique solution, imagine part of them. Being positive, if you take the boundary value of the imaginary part of the place, then out of this procedure, you got functions which have the following properties. It's supporting a Hamiltonian intervals that you are reanimated after whenever it's non-zero. It's not that surprising, but what is surprising is that the singularity structure, the way how it goes down to 0, it can go down only basically two different ways. Either it goes down the regular edge, the square root singularity out from the semicircle below, or it can go down at a cubic path. And there is nothing there. Now, this is important because remember that the corresponding universality statement, so if I look at this deterministic analysis, but now I look at the corresponding random matrix, and these rows is supposed to be the density of the equilibrium density of the corresponding random matrix, and then the local statistic depends on which is the singularity path. And then you have a theorem which tells you about basically two types of singularity edge of cubic path, but nothing more. Now you have only two types of universality, and indeed this Tracy-Widom at the regular edge and this Pearson distribution. Okay, so now let me show a little bit what is the basic tool. How to prove things. I'm not going to prove anything, but to give you a little bit feeling. So there is an absolutely important tool in this whole business, which is called the local law. Local law says it raises the resolver. They take the H is random matrix, you do the usual resolver, Z values from your pattern. And the surprising fact, and the very basic fact about random matrices, that the resolver tends to become deterministic in a certain sense. So H is random. H is a completely random object. Every matrix is random, but when you do this thing, you take a 1 over H minus C, and this is of course a matrix, a random matrix, But this random matrix tends to be deterministic, converging the deterministic object exactly the law of large number we do. So here's the work to solve. Yeah, and its limit is this M. So the M what we solved in the previous page, in this complicated procedure, this M had a meaning, this number because it gives us to the density of states. The meaning of the M is that this is the limit of the level. And there are precise theorems which tell you how to do that. So you take the G minus N, so G is the random object, M is its implicit closed limit. Of course, you have to define the sense of convergence in such a way that it holds. So I do it in a weak sense. So weak sense, G minus N is a matrix, and I'll test it against another deterministic matrix B. And I look at the average, bracket is the average case. And then this difference is getting small. And small in the following way, it's small by 1 over n times eta. Eta is the imaginary part of the z. Now, you can imagine that as the imaginary part of z goes smaller and smaller, z approaches the real axis, then the resolvent becomes wider and wider, more crazier and crazier. Yeah, it is very much inside the spectrum, so no standard calculation theory would work. But nevertheless, as long as the eta, which is the imaginary part of z, is a little bit bigger than 1 over n, we are very, very close, n is a big number, very, very close inside the spectrum, close to the real axis, then still this m is a good approximation to g, this is a bit the one the speed of convergence. And there's another version that can be tested against the So that's the rest of the local class numbers for the result. And it has many corollaries. Let me just list two of them. One of them is what we call the rigidity. It tells you that the eigenvalue, the true eigenvalue, these are the lambdas labeled in an increasing order. The true eigenvalues are very close to where they should be. Now, where should they be? If they were really distributed by rho, then you look at the nth quantile of the alpha's quantile of that distribution. So you integrate the rho from minus infinity up to this level gamma alpha, so that the weight is the total mass of over n. So this defines the sequence, deterministic sequence of numbers. And the claim is that the lambda is very close, but it's as close to that as the typical level of spacing, which is 1 over n. But unfortunately, in the bulk of the adjective to be different, but more than it. So it tells you that the eigenvalues are very rigid. The eigenvalues are random objects, but they are still very close to where they should be, the deterministic value. It's 1 over n close, so it's as close, basically as close as the level of space. The eigenvalues don't fluctuate. And if you know how the Poisson process behaves, then you should know that the Poisson process fluctuates. No? Square root of every current continuation. Which are very rigid systems. Another corollary is the eigenfunction delocalization, which I already mentioned before, the localized eigenfunction. So in this mean field model, eigenfunctions are completely delocalized, which means the following: you take u alpha is one of the normal eigenfunction, and then you test it against a deterministic vector x. And then the overlap, the scalar product square, is a order 1 over n. So what does that mean? This means that the u alpha is completely random. If you do a little calculation, you take a completely random vector on the unit sphere, an n-dimensional unit sphere, completely random vector, then the projection is completely random vector at any given vector x, really very small, and high-dimensional entry vectors are almost overlap. So if you take a random vector on the unit and on the n-dimensional sphere, and you project down to one direction, this projection is 1 over square. And what it says, so this is completely random, and what this theorem says is the eigenvector is completely random in this set. Completely Now just one, because every talk should include one proof, so the unknown proof of this fact, given we know everything else, given we know the rigidity, just a feeling how one uses this local laws. We want to understand this overlap square, okay? Now you extend it in the following way, you're smuggling, you put it into a part of a big sum. So you put in a sum where you take this overlap times this factor. This is like a Cauchy factor eta over lambda minus lambda plus theta. And then here the gamma is of this quantized. So this is a triviality because we know that the alpha minus gamma is a order 1 over n. We choose the eta to be 1 over n. So eventually this factor we have an order factor for that particular alpha that we are interested in. And for every other alpha, this factor is actually quite small. Cauchy curve is equal. You do that, so it's an overestimate, an obvious overestimate, but it's not a too bad overestimate. And then once you have this sum, then with the spectral theorist, you immediately recognize that you see here is nothing else than the imaginary part of G, evaluated at this gamma alpha, which is a big number, and evaluate plus our eta, and this XX matrix, so you can put that on the English alpha. So that's spectral theory. And the other hand, if you know the local law, then this version of the local law, then this tells that the imaginary part of G can be imaginary part cheaply. The take the imaginary part of Gxx is bounded by the imaginary part of Mxx plus the alpha. But both of them are order 1, so in particular we have an upper bound on the imaginary part of Gxx. But the important thing is you have upper bound down with very small weight. This is unusual. Like that is all done. And you go down with the spectral parameter, there inside the spectrum so close that to the spectrum is 1 over n close to the spectrum. So typical resolvent is lower, but this is a random resolvent. It doesn't work. It's a target from very strong effect. And in particular, as you see from this one, this count. Okay. So far I was talking about mostly eigenvalue, except for this one, the localization story. Let me talk a little bit about eigenvectors. There's a universality picture, question about eigenvectors as well. This goes back to something which is called the quantum universality and quantum chaos. It's a little bit different topic, but these pictures are very nice, so I should show them to you. So behind that, there's another big conjecture, big vision. The quantum chaos conjecture, it says the following, that we have classical and quantum dynamics. The top two pictures are classical dynamics. These are projectors with a single particle moving that according to the usual simplest rule, uniform motion plane, one single point particle. It said that it's a billiard, so it bounces back on the boundary of the billiard table. The first one is a two-dimensional spherical billiard, and then the trajectories are very regular. It's an integral system, very simple linear system. The first integral is the angle here, the angle of incidence, that remains constant under the motion. And so this is because it's a very symmetric system. So if you destroy a little bit the symmetry, so this is a RBO shaped billiard table, but basically anything that you do with any disturbance that you do with the nice symmetry, very symmetric case, you create immediately very different pictures. You create a chaotic picture. So it's a billiard conjecture. So it's a very typical, very general fact, not a mathematical theorem, but it's a physics facts that systems, classical systems are either integrable or chaotic. And now we quantize them. So there's a procedure which tells you how to create quantum mechanics out of classical mechanics, which means that instead of talking about the classical Hamiltonian or Lagrangian, you will quantize it and you will talk about an operator, a self-adjoint operator, and then you start asking about eigenfunctions and then so the correct quantization of a billiard, of this kind of billiard, is a Laplacian on the corresponding domain with the appropriate eigenoperator. What you see in the picture down is an eigenfunction, a high energy eigenfunction, corresponding to high eigenvalue. It's an eigenfunction of the Laplacian with normal boundary condition under this. And again, you see a nice symmetry. The rotational symmetry from upstairs is inherited in the quantum picture. While in the other picture, when we have a chaotic system on the Tesla where the corresponding quantum wave function was appeared. It's a mess. So now we have this dichotomy, and we would like to understand the very general question, the quantum chaos question. Is this picture true in some true generality? Now, of course, we do random matrices, so we don't exactly have a corresponding classical picture behind that. So this is only a motivation, but the message that will come up in the next page is that random matrices are in this category, but they correspond to chaotic wave function. So it's as chaotic as possible. It's not very surprising to random matrix. So this is what the universality of the eigenvectors expressed in mathematical terms. Look at the orthonormal eigenbasis of it, and we expect this as random as possible. Now it's an orthonormal with n orthonormal vector, so the orthonormality has to be respected. So modulo this orthonormal coefficient, the most chaotic, the most random, most random n tuple of n vectors of combination orthogonal vectors with the half distributed. And you can put that like a quicker, the diagram as possible, the corresponding. So this is what this should be true, and this is the conjecture that the eigenvector, the random matrix behaving this very general ways to about this distribution. Now it turns out that in the Gaussian this is trivial, and this is an algebraic fact. Simply because the Gaussian ensemble happens to be invariant and a unitary conjugation. Matrix which are Gaussian matrix, invariant Gaussian matrix, and you conjugate them with any unitary matrix U and U star of the fixed size, you do the infinite application, you get a matrix with matrix elements are still Gaussian or not self-recurring, but the matrix elements are still independent. With your calculation, and only the Gaussian matrix can do a typical distribution of the factor of independent matrix, and the sandwich between two unitary and Gauss can be not Gaussian. So this means that the eigenvalues, the eigenvectors, because you diagonalize your Gaussian matrix, and then the eigenvectors which are form an unitary matrix, this is independent of the eigenvectors. So based upon this symmetry, it's easy to see that the more argument, it's easy to see that the Gaussian case, the eigenvectors must be completely chaotic. But then as the typical universality statement predicts, the same statement should hold, a similar statement should hold, maybe not in an identity, but the limiting statement should hold for any determinant, and without Gaussian. So for example, by various aspects of that, instances of that. For example, you can ask the following question. You can take an eigenvector Ui as an eigenvector, and you can evaluate its one of the matrix elements. Because the third eigenvector, say the fifth matrix element, the fifth entry of the third eigenvector. You have to normalize it as square root of n. This happens to be Gaussian. That's part of the really hard distribution. Very easy to say it's a simplified Gaussian. And in that case, I can prove that origin was not GE, it's the Gaussian, and it's also true in a joint distribution sense. You take the fifth element of the third eigenvector and 10th eigenvector more, and then with three random numbers, both of them are Gaussian, and they're also joint independent. So this was done earlier, and then this is an extended version of that, a more general version of that, which is analogous to which is the same thing in this quantum universalism, where you do this in the following way. You take a deterministic matrix A, think of the observable quantum mechanics, and you sandwich this A between two eigenvectors, the I and the J eigenvector, this configured quadratic form, and then you ask how this quantity behaves as angles can think of, what's various in a probabilistic sense, and very hard to think how it looks like. And surprisingly, what comes out is that this becomes a diagonal matrix times the average space of A, plus there's a little fluctuation at the top, which is Gaussian, Gaussian thing, but it has a sine 1 over square root of n. So if you look at this statement here, morally, I'm just going to explode on it, This statement looks like a central unit here. The first term is like a law of large number. This is a random object, which has a deterministic leading term, plus it has a fluctuating function of type 1 over square root and the type of the fluctuation is optional. So it is in this picture. And I mean, there's a story behind that related to that, to this beautiful picture about the quantum curve. Thanks so much about that. And then there's another version of that which concerns the extreme statistics, which leads the Gumbel distribution. Let me say a few words about something else, about the non-Hermitian world. So what have we dealt with the Hermitian matrices and the large part of the theory about Hermitian matrices, but you may wonder what happens for non-Hermitian matrices. It's kind of the last few minutes on that. So the prototype model is of course very similar. Take an IID matrix, n by n. The only thing is that now the entries are truly independent, so there is no symmetry between x1 to x2 and conjugates of each other. As random as possible. And of course, it's not self-contained. The eigenvalues will be genuinely complex numbers. And this is how they look like. So this is n equal 50, I think. The first picture is about the real case, when the x's are real random numbers. Second picture is about the complex case. The two pictures look more or less similar. We see a bunch of points in the universe. Of course, if you look at it a little bit more carefully, you see a difference between the left and the right. Check it with tirelessly. What kind of difference you see between the left and the right? And that's very good. So one of them is this one. So of course, in that picture you see. So in the real case, you see a symmetry on the real axis because the eigenvalues of the real matrix coming back. It was something. What is the other one? There's one more thing which you will see. And you know, we could be better eyes on that. Which relation? Some accumulation. No, this you don't see anything, you know, something else. You won't buy the fellow see. Yeah, that's an accident. Yeah, that's like it should not be. But there's something wrong. More wrong. It's the fact that there are real eigenvalues. You see in the real case there are 5 or 4 or 5 eigenvalues on the real axis. Real axis plays a special role, not because it's symmetric. Because the real eigenvalues, this is expected and it's a characteristic polynomial and then we polynomial here. But a real polynomial, but of course there's nothing like in the complex. The complex picture is completely translated, rotation invariant. In the first picture, the real axis plays a special role. But not apart from that, the two pictures are very similar. And now if you start increasing n, then you see a very nice factor. You just get denser and denser, but you see immediately that the eigenvalues remain very strictly within this. And also you see that the density is partly constant. Okay, the picture. And indeed, that's the low large number level of this picture. That's the analog of the Wigner-Dyson circle. That is the circular law. It's formulated here. It says that the convergence of the empirical distribution of the eigenvalues, if it converges to the uniform distribution, exactly on the chess, so here and there. Now the eigenvalue spacing is now a little bit different. Earlier the eigenvalues were distance of 1 over n. It's a three-dimensional picture, so if you have endpoints in a unit distance, but you could have this kind of different point and its neighbor closest point is n to the -1/2. So the scaling will be different. We're going to draw the local statistics, but again the moral of the story is the same. So here's the pictures showing here pictures. So what we expect is the following: that if you zoom it out, and by appropriate scale, the appropriate scaling to square root of n, but to zoom it out in such a way that you see a genuine point process, so that the distance between neighboring point is over 1, and then those two infinity. Then what you see a point process, and then this point process becomes universal. As a statement. Again, you can format it in terms of correlation functions. You can format in terms of gas because no meaning of last eigenvalue, but total correlation function conformity. And again, you see this phenomenon that the edge, if you do this picture with zooming out at the edge, and the statistics at the edge is different than the one. But apart from that, it doesn't matter where you are on the edge, doesn't matter where you are on the one, except if you are in the real case and you look at near the real axis, because of the real axis that is a special role. So this is seen the universality. But most importantly, all these pictures are independent of the choice of the distribution there. The distribution matrix. That's a very universality picture, and it's called the edge case was together with George and Dominic. And then the light universality to Barters, which was further, actually done 2 years ago. So the analogous universality statements for eigenfunction, eigenvalue, the non-Hermitian case can also be proven, but actually the corresponding Hermitian case. So in this slide, I will just summarize the state of the art. Basically, what I said before, and I should stop. So that's the state of the art of the Hermitian versus the non-Hermitian situation, a very high level. So in the Hermitian case, the prototype is always the Gaussian thing. So prototype meaning that you read up the answer. Usually Gaussian is computed, but read up the answer can be Gaussian, and then you go towards the IID situation. It's not Gaussian. The answer is always the same for the Gaussian or to prove it. So this is the Hermitian case, and then we know the semicircle, like the low class number level. Then we know the local statistics, which is roughly speaking, the sample universal fluctuation, or the type of the fluctuation like Gaussian, that we found there, but it's a universal thing. And also we have the corresponding statement about the eigenvectors. And if you ask the same question about the non-Hermitian situation, then there's again a Gaussian prototype. So just check out the Gaussian. This is called a Wigner matrix, which we figured it out. And then here by now we know the circular law, the law of large number level. By now we also know the local statistics, very recently that. But we don't know the corresponding eigenvector, because it's back to the eigenvectors, multiplied by overlaps, are also universal, given by the corresponding distribution to an open question. And then this is what I formatted here, strictly speaking, was IID, and according to this picture that I showed about this S matrix, Dyson and so on. One can also ask the same question for more than situations for relative matrices and so on, and let me not list more results, but basically in the Hermitian case, it's almost everything is done. Non-Hermitian case is not yet, but this is sort of one direction in what we are working on, try to generalize these statements, these universality statements, more bigger classes of and let me just close with this sentence here, this general pattern, is that the way how one proves these things is that there's a steep path. One of them is the Gaussian calculation. So if you think of the Gaussian model as something which is explicitly computed, but explicit computation is basically easy computation, but something very complicated calculations. It involves a huge beautiful mathematics involving orthogonal polynomials, lots of things happening there, but that's one big chunk of one. Do explicit calculations. What are the fine question you can ask? There is the first thing to test it with the Gaussian, what can be complete. Sometimes you can something different. This is one type of business. And then the other type of business, which are more involved in and not so much involved in active calculation, I'm more an analysis person, is that to try to prove that if you depart from Gaussian, if you take the value distribution, any other distribution, and you take some correlation, anything like that, then the universality answer to its universality question is still the same as the Gaussian. The Gaussian matrix for which you know the answer, and we have IID like non-Gaussian, for which you don't know the answer, and we want to compare everything. And the only message that I want to convey here is don't think of it as a calculation. You may think of it as Gaussian, non-Gaussian, that approximate the Gaussian, the non-Gaussian, the Gaussian. You replace the matrix elements one by one, keep on replacing, maybe keep on for the non-Gaussian matrix and start replacing the Gaussian updating that, object which is computed. But this is some kind of perturbation here. The argument is like it very much. But this problem, these questions are well available. So just imagine that typical size of a matrix element is 1 over square root of 1. If you just change one matrix element and one matrix from another, then you will change the problem and the square root of 1. On the other hand, the type of question that we are asking is much finer. In this eigenvalue statistics, this is on the scale 1 over n. So trying to understand the eigenvalue thing of 1 over n. So if you do a perturbation theory of order 1 over square root of just one matrix element, this are discrete of it. That's the format for the target decision. Not even mentioning that you have to do not just one matrix element, but you can scale. So it's a very, very much think that's the methods on basically it is not a perturbation. Okay, so I think that's basically maybe that's the last part. Put it in yesterday. So that's the last slide where I just want to mention the scales, and the scales were already mentioned before in some sense. So the basic object very often the resultant that's catches the eigenvectors, eigenvalue of the eigenvectors, and what is the precision of that depends on the imaginary part of Z. So the imaginary part of Z is smaller, the smaller it is, the more precisely we approach to individual eigenvalues. So there is a scale which is for the mesoscopic scale. When you ask a question involving not just one eigenvalue but a cumulative of more than one eigenvalue. The extreme situation where the Wigner-Dyson approach about all the eigenvalues at the same time, you can do somewhere in between all that and the other. Now, as long as you are in this mesoscopic scale, then this local or this idea that the resolvent becomes and this is the key workhorse tool that the basic method that we use in the proofs, because there is when the resolvent become deterministic as long as this 1 over n is convergent, as long as the 1 over n is small. So as long as the eta, imagine that is much bigger than 1 over n, these methods and there are various to exploit them. But then there's another version, another stage because the microscopic scale, when the eta is so small, for the 1 over n even smaller, so small to start seeing individual eigenvalues. That's a completely different question. But in vector, you don't expect any more than the resolvent become deterministically don't become anything else. So they're too strong with the eigenvalue here. So then we need completely new method. And this is just listing the 3 major methods. Actually, this is the regime. Like 3 major methods, one of them the famous Dyson and motion, which is a linear approach that is a slightly stochastic differentiation for the eigenvalue. This is what we use in our proof for the universality. There is a very different method for the supersymmetric formalism, which is a fascinating thing if it comes from original ideal in physics. It's very hard to make it mathematically rigorous. It's only very few cases that we could make it mathematically rigorous. Although it's completely clear that the calculation that cheaper or large generality, but again, mathematicians many apart from the physicists. And then there's a new method which is called the partial Schur decomposition method, which is very recently the dark universality argument or the alteration. So these are sort of the overview of the method that we studied.
Very much for the very nice talk. So now I guess we can stop recording and have some questions.